Building on what we already know about position tolerances, now we're going to take a look at a set of features, in other words, a pattern which we see in numerous products. So for instance, here we can see the keys on this piano arranged in a specific pattern. And how can we describe that entire pattern in terms of being able to control position? And patterns frequently occur on many different types of products, as you've probably seen. So we'll look at controlling the position of the entire pattern, not just individual features by themselves, and that tells us there's a relationship there. What do these pattern tolerance zones look like, and also what is the effect of using material condition on these types of patterns? Well, we see here a bunch of different patterns, and we could group together, for instance, our 4 cylinders on this engine block, or we have cooling holes and mounting threaded holes that we could describe with a pattern. Now the thing about a pattern is we've got features that are repeated at different locations, and there's this relationship between those features in that fixed pattern. So for instance, we want to make sure that we have the same separation between the 4 cylinders and that they are positioned along a center line. Well, we can control that with a geometric tolerance. The tolerance zone is for each feature in the pattern. And so essentially I've got this composite tolerance zone made up of individual tolerance zones. So here's a simple pattern of 4 holes, and you can imagine we've got a plate here that we're going to bolt to another component, and we want to make sure that these 4 holes line up with the corresponding part. So we know we've got a 4-hole pattern, and how do we describe it in terms of location? Well, we think of our tolerance zones just the way we did before. We have a position tolerance, and that's indicated, of course, in the geometric tolerance zone. We're looking at position, and we have an indication of a pattern 4 times. So you wouldn't want to repeat this feature control frame 4 times on the design spec. We want to control a pattern of 4 holes. So this applies to all 4. The same concepts of size of the tolerance zone, same concept of datum reference frame. So now what we'll do is establish our datum A, which would be a surface plate to find that surface, and then surface B, which is this outer cylinder. We'll use the mating envelope, and we'll construct that so that we have an axis corresponding to datum B, and we're saying here that the pattern has to be centered on datum B in terms of the location. Well, what does that really mean in terms of the tolerance zones? We have 4 tolerance zones put together to describe this pattern. In order to locate the tolerance zones and orient them, we have to look at them individually and how they're related. Well, first of all, we know that we're going to orient them perpendicular to A, each one of these. And then the question is, how are they located? Well, we need to look at basic dimensions. And so we note the basic dimension of the pattern is 6.5. So we have this cylinder here, and of course we're looking at it in 2D, so it appears to be a circle, that tells us the tolerance zone should be on that cylinder. So when we orient it perpendicular to A, we're going to have the separation between these of 6.5, or you can look at it as a distance from B to each of these holes to where we're going to put the tolerance zone, and that would be 1/2 of 6.5, so we have 3.25 from B. But that's not sufficient to describe the location, because obviously if I just say 3.25 from B, we could have them all next to each other down here, and they would satisfy that location. The other basic dimension is the angular separation. So we have 90 degrees between each tolerance zone located at a distance of 3.25 from B. That's how we describe the location of the pattern tolerance zone. Well, we can also look at a pattern in terms of the relationship of individual features, which we just saw, and we can look at it from just the features themselves and not be concerned about where the pattern is located. If you do that, then you're going to be using a composite tolerance zone, and a composite tolerance zone looks like this. It actually looks like two feature control frames. It really is only one, but we have two variations of that geometric tolerance. Now the first one, what we call the pattern locating tolerance zone, that is the top, and that's what we just described in the previous slide. That talks about the pattern relative to other part features, in this case datums A and B. And then we have another way of constraining the location of features relative to each other, and that we call the feature locating tolerance zone. Note that the value in terms of the tolerance zone size is strictly less than the size of the tolerance zone for the pattern itself. So what's the major difference here? Well, what you should note is there's no B, so the datum reference frame has changed. Here, A provides a constraint, and that is orientation. So we're only concerned about how the tolerance zone for the feature locating tolerance zone is oriented, and we're not worried about where it's positioned. So let's think about our composite tolerance. What is the net impact of that? Again, the top one, the pattern locating tolerance zone, we're going to have a set of zones, and so we have this zone pattern. The pattern must lie within the zone, the entire pattern. And this is the primary difference between this and the feature locating tolerance zone. That zone location is fixed at true position. Whereas for feature locating tolerance zone, the position is floating. So there is no true position. We only fix the tolerance zones relative to each other. And so we're not so concerned about where the pattern is as much as how the features in the pattern are related to each other. Now, as I said before, the size of this tolerance zone is smaller, and so it's a further restriction on the relationship. So here's our example, but now we've added a feature locating tolerance zone, as you can see here, which is more restrictive. What is the net effect of that? Well, first we have to compare the pattern to the pattern locating tolerance zone, and if that is satisfied, then we're going to take a look at the feature locating tolerance zone and see if it satisfies that constraint. So it's going to look something like this. If I look at the pattern itself, and I've drawn it as a grid work here, we are locating the pattern at true position, as we described before. 3.25 units from B and separated by 90 degrees. Now this pattern as a whole can move as long as all four axes of the actual holes fall within those four tolerance zones simultaneously. Again, that's the relationship of a pattern. So if that's true, then we see that we're centered on B, the pattern is, and also parallel to B, or you can think of it as perpendicular to A. So we're allowing that pattern to move around a little bit, depending upon the size, in this case 0.02 for the tolerance zone. What about the feature locating tolerance zone? Now we forget about the pattern, and so I'm not worried about that in terms of where it's located. I'm only concerned about how these individual holes are related to each other. So it may look the same, but the difference is I could be anywhere. In other words, this is not fixed. I can translate the location of the four tolerance zones as long as I maintain this relationship between the four. Again, we're separated by 90 degrees, and we are on a cylinder, but that cylinder can move anywhere on the part. Of course, the size of the tolerance zone is half the previous one, and therefore it's a tighter constraint on these relationships. So now I can move this around as long as all four simultaneously fit within the tolerance zone. My only constraint is they have to be perpendicular to A, and they have to be fixed relative to each other. But for the pattern itself, there's no location constraint. Here we've got the use of material condition as we've seen before, and we see a 3-tab pattern here where I've got a tab feature and 3 of them. What we're trying to do is control the position of those. Well, you should recognize, first of all, that we have a pattern, and secondly, how are we going to control the location of the features? We need some locating geometry. So in my pattern, I'm looking at 3 tabs, which really means I'm looking at the 2 surfaces. Well, of course, we have to reduce that to 1 locating geometry, and as we've seen before, in this case, we're going to have a plane representing the tab. So the plane representing the tab is going to lie within 2 parallel planes. That's the shape of each of the 3 tolerance zones. And those are separated by a width of 0.02. That's the static part. The actual width of that tab, D, which we would measure using the mating envelope. And then we also have material condition on B, and B, as we see here, is solid, so its MMC is 2.6. We find B in terms of a mating envelope, and of course when we construct B, it's secondary, so it must be oriented with respect to A, and that gives us the axis here. So we're going to line up our tolerance zones so that they are centered about planes. Again, we have to put this at true position, right? So we're going to have a plane coming out from B, and then we'll center our 2 planes about that plane. So as you can see, I've got 3 tolerance zones at true position, and of course they're separated by 120 degrees. Now I can compare the location of the midplane by taking the mating envelope, determine the actual midplane, and see if it falls between each set of 2 parallel planes. Note again, we are fixed with the pattern locating tolerance zone at that point. The feature locating tolerance zone, we drop the restriction, datum B, because we're no longer interested in the location of the pattern. The shape of the tolerance zone is the same, 2 parallel planes. We don't have material condition in this case, so we are going to fix 3 sets of planes so that they're separated by 120 degrees. That is the only restriction in terms of relative location. And secondly, we're going to orient them so that they are perpendicular to datum A. Again, the size, the width of the tolerance zone is smaller, and so it's a tighter restriction of these tabs relative to each other. So at this stage, you should understand the concept of a composite tolerance, and by that we mean we're looking at a pattern, and that pattern can have 1 or 2 geometric tolerance zones in that composite tolerance. The first one would be the pattern locating tolerance zone. That ensures that the pattern itself is located correctly. And then the feature locating tolerance zone ensures that the individual features are constrained relative to each other. So in summary, your tolerance zones in a pattern are not independent. They are related to each other. And it's important to maintain that relationship. If I'm looking at the pattern locating tolerance zone, it's fixed at true position. Whereas the feature locating tolerance zone can float, of course, we have to maintain individual tolerance zones relative to each other. And material condition, as we've seen, can be used in the pattern tolerance zone.